What is a decollement? Decollement comes from French for detachment coming unglued. In geology, it is used to describe a fault surface that separates deformed rock from undeformed rocks beneath. Essentially, weaker bedding planes with low friction act as slip surfaces, which can make thinner wedges and promote back thrusting. Stronger bedding planes promote thicker and more stable wedges. To demonstrate this, we will use a sandbox model to test our hypothesis about how decollements of varying lithology affect the geometry of the propagating faults. To start, our control sandbox was constructed using different coloured homogeneous sand in layers. Sand is a good material to use for this experiment, as it similarly mimics the deformation rocks go through during orogenic events. Our control variables for this experiment were the total thickness of the material at 4 cm and the total internal length of the box at 28.5 cm. The data measured through both experiments include the number of faults and their angles and the wedge height and length. This image of the final result shows that the homogeneous sand created brittle thrust faults within the sandbox. The youngest faults propagated at an average angle of 26 degrees, and the maximum total wedge thickness was 8.5 centimeters. Our second box was constructed using talcum powder as the decollement layer. Talcum powder has lower friction than sand, allowing it to act as a weaker bedding plane. In this experiment, we have a back thrust developing. Two back thrusts formed in the second experiment, both in the opposite direction than the main thrust propagation. Due to the talcum powder smearing on the glass, we weren't able to accurately measure their exact dips throughout. But the first one measured at 34 degrees on its first appearance at 5 cm shortening. The tips of both the youngest fault and the top surface, or alpha angle, were shallower in the sandbox with the weaker decollement. There wasn't much variation in the position of locus, maximum wedge thickness, or wedge length. In the second box, the youngest had an average dip of 20.8 degrees and the oldest of 42.75 degrees. Our hypothesis was based mainly on two studies, one by Bourvil et al., who tested the impact of decollement dip and strength on fault vergence, and one by Mahmoudpour et al., who investigated the influence of material strength and friction on back thrust development. We were interested to find out if we could influence the development of back thrusts and of the overall geometry of the thrust faults by changing the decollement strength. We only used one variable in our experiment, strength, but some of the results line up with both of them. Bourvil et al. Found that back thrusts form in orogenic wedges with weak decollements, and that's what happened with our second sandbox. That said, they also stated that weak decollements alone do not suffice to explain systematic back thrusting. In addition, basal dip must be very shallow. Another thing we can agree on is that stronger decollements result in higher taper angles. But their following statement that fore thrusting is more favourable in the stronger decollements is one that we'll have to take their word for, as we had the same amount of fore thrusts in both. Mahmoudpour et al., on the other hand, stated that an increase in decollement strength, and therefore friction, is the main driving force behind back thrusting. The secondary part of our hypothesis concerning the geometry was based less on past research and more on our own curiosity. We just wanted to see if the wedges would change shape depending on decollement strength. The good news is they did. The flats of the ramp and flat thrusts were flatter and more elongated in the sand-only box and angled down and shorter in the sand and talc box. This is the exact opposite to what we thought would happen. We had assumed that due to less friction in a weaker decollement, the horses would be capable of moving further over the foreland than they would over a stronger decollement. That said, the experiment could be redone with different materials, different shortening distance, and varied dips to get an absolute confirmation on these findings.